and welcome to our second lecture on the theory of time. If you recall from our first lecture, we talked about the Romeo effect. What was the Romeo effect? The Romeo effect is drawing conclusions based upon false assumptions. And we looked back at the story of Romeo and Juliet by William Shakespeare, and we looked at the point in the play where Juliet was fainting death. Romeo, thinking that Juliet was really dead, then decided to commit suicide, only to have Juliet awaken. And so Romeo had a false assumption. That false assumption was that Juliet was dead. And as a result, he made a bad decision. He committed suicide. And what we did was we compared this to the assumptions made by Albert Einstein when he developed his theory of relativity, both the special theory and the general theory of relativity. And we said that Einstein had three assumptions that he made. One assumption was the principle of relativity, and that is the subject of this lecture. The next assumption was the principle of invariant light speed. That will be the subject of our next lecture. Finally, there was the principle of four-dimensional space-time. That will be the subject of our fourth lecture. In the theory of time, we're going to disagree on the principle of invariant light speed and the concept of four-dimensional space-time. However, we will agree on the principle of relativity. So let's review for a moment what is this principle of relativity. Einstein looked at relativity as in outer space, there is no end to space. There is no absolute space. Space continues on in every direction. Nothing in the universe is standing still. Every object in the universe is moving relative to the other objects. And in fact, he says that in every frame of reference, a frame of reference surrounds an object in space, that every frame of reference is in uniform motion to every other frame of reference. Now, not only this, but every object is moving under its own inertia. Okay, so what was inertia? Well, if you recall from the last time, we're throwing out gravity here. Gravity causes things to accelerate, to change paths, things like that. Without gravity, then the heavenly bodies can only go in a straight line, and they will go forever at a constant speed because there's no force acting upon it. This was Newton's first law of motion, that every object in motion will stay in motion unless acted on by a force. That force would be gravity, but we are excluding gravity in these inertial frames of reference. Einstein further went on to say that within every inertial frame of reference, the laws of physics are the same. And in the last lecture, we talked about the speed of light. That in every inertial frame of reference, the speed of light was measured to be exactly c. As a result, since every law of physics is the same, one cannot tell through experimentation in which frame of reference they exist, because they're going to get the same results in every frame of reference. So therefore, they cannot tell in which one they exist. Finally, Einstein's going to argue that space and time actually go together, that they are very much dependent upon them. And he called this concept space-time. One word, space-time, where space and time are very much dependent on each other. So that was Einstein's view of the principle of relativity. And we can illustrate this in a diagram. And as you see down at the bottom, we have a person standing on the planet Earth. Okay. We can have one frame of reference acting like it's standing still. Typically, this is the observer standing on Earth. So this frame of reference that includes the observer on Earth, we're going to call the at-rest inertial frame of reference. It's at rest because we're going to measure all the other frames of reference relative to this one frame that we're going to consider to be at rest. Above the Earth, we have three different people in three different frames of reference. They're all moving in different directions and at different speeds. But they are all moving in straight lines and at constant speeds. Their speeds are not changing because there is no force being applied to them. So that's the idea of Einstein's inertial frame of reference. All right, so we've talked about what is the principle of relativity. Why are we going to now go have a whole complete lecture on it when we agree with it? The answer is history is important. We need to understand how this whole idea came about so that we can understand how Einstein was thinking when he chose his assumptions. So we're going to look in this lecture at three components of history. One is how the nature of the universe was developed over time. We're going to go way back to Aristotle's time and look at the geocentric and come up to Einstein's time where we had something called the galactocentric universe. We're going to look secondly at how the principle of relativity developed within the context of this nature of the universe. Why did we have the principle of relativity? Finally, we're going to look at the nature of light, and in particular, how light relates to the principle of relativity. Because when we get to the next lecture, when Einstein argues for the invariant speed of light, we're going to look back and say, hey, maybe there's another alternative. So we're going to look at the nature of light. So that's our goal here in this lecture. Look at the nature of the universe as it evolved over time. Look at how we developed the principle of relativity, and look at the nature of light as it developed over time. So we're going to start this journey through history by going back to the time of the ancient Greeks. In particular, we're going to go to the 4th century before the Common Era, at the time of the philosopher Aristotle. Now, Aristotle is standing in Athens, Greece, and he's looking about him, and he's thinking, I'm standing still. The earth that I am standing on is standing still. Now, we'll assume there's no wind pushing him around or anything. So as far as he can tell, he is not moving. Therefore, the earth is standing still. Now, if he looks up, he's going to see the sun moving from east to west across the sky. He's going to see the moon moving from east to west across the sky, maybe at different times than the sun. He's going to see a pattern of stars and constellations that at night move across the sky from east to west. And he's also going to see these special moving stars that go from east to west. And they'll have names such as Mercury, Venus, Mars, Jupiter, and Saturn. And so what is the Aristotelian view of the nature of the universe? Well, it's that the earth is standing still. And above him are these crystalline spheres that are orbiting around the earth. One crystalline sphere holds the sun. Another one holds the moon. Another one has these constellations that stay in formation. And each of these moving stars, Mercury, Venus, Mars, Jupiter, Saturn, each have their own crystalline sphere that is moving across the sky. So the fact that we have one crystalline sphere out there that has the fixed constellations says that our universe has an endpoint. The Earth starts here, it goes out to that crystalline sphere of fixed stars. Well, if I knew how far away that sphere was, I could measure a volume for the universe. So that's what we mean by an absolute space. The universe has a very set volume. Now, in addition to that, there's a question of what fills the area between these spheres. We know here on Earth that we've got air. We can see through the air, but we can feel the air. And we know that sound has something to do with air. but does air fill everything between the spheres? And the ancient scientists felt that, well, rather than air, there was probably some substance, and they called it ether, that filled the heavens. And that idea is going to be around for a long time, because it's going to take a long time before anybody can design an experiment to determine whether or not there is ether up there or not. But at the time of Aristotle, we had absolute space and we had ether filling that space. So let's go forward 600 years to another Greek. This Greek was living in Alexandria, Egypt at the time, and his name was Claudius Ptolemy, and he lived in the 2nd century of the Common Era. Now, by this point, a couple of the areas of philosophy had broken off into their own sciences. So there had been enough research on the stars that we had the science of astronomy. There was enough philosophy on the nature of numbers and operations on numbers that there was a field called mathematics. And so we're going to see that a lot of these people that we are going to look at are both astronomers and mathematicians. And Ptolemy was one of these people. Now, we've had 600 years of observations of the sky, and scientists had noticed that these movable stars tend to have what is called a retrograde motion. So what's a retrograde motion? Well, let's take Mars, for instance. Mars is coming along from east to west, and all of a sudden it will stop, it will reverse direction, head back east for a little bit, stop again, reverse direction, and continue to the west. That's a retrograde motion, where it comes, reverses direction for a little bit, and then continues westerly. And what they observed was that all of the moving stars had this retrograde motion associated with them. Well, as scientists, they wanted to explain this retrograde motion. Now, Ptolemy was very much still believing in the geocentric model of the universe, that the Earth was standing still at the center of the universe. So, let's take in Mars. Mars isn't just going around the Earth in a crystalline sphere. Instead, it's going around and making little loops as it goes around. These loops are what's going to cause that retrograde motion. Well, the question then is, well, what's causing the loops? And what Ptolemy came up with was the idea that associated with each one of these moving stars was another black body, something that we can't see. You know, it's the original dark matter. This is something scientists tend to do, is if they can't fully explain their theory, they invent something to explain the theory. And what Ptolemy invented were these little black bodies. And Mars was orbiting around this other black body as it orbited around the Earth. And so this other black body was causing the looping of Mars as it went around the Earth. Now, Ptolemy put this into a publication called the Almagest. It was published in the 2nd century, and it was a mathematical model which predicted many things about astronomy, the heavens, and in particular, it predicted when we had these retrograde motions. When you have a mathematical model to support your theory, there's a lot of people are going to believe that you know what you're talking about, that you have the truth of the situation. And this Almagest, with these looping orbits, this geocentric model with these looping orbits for these movable stars, was around for 1,400 years. All the way from the 2nd century up to the 16th century. So what happened in the 16th century that changed this? Well, we have another astronomer, mathematician on the scene. His name was Nicholas Copernicus. As I said, he's a mathematician, astronomer. He's also a Polish Catholic clergyman. In the 16th century, we were in the heart of the Middle Ages. And in the Middle Ages, we had the three-estate system, where you had the nobility, you had the clergy in the middle, and you had the peasantry at the bottom. and the clergy in the middle was the educated class. And so Nicholas Copernicus was part of this clergy that was educated. And one of the things he was taught was the Almagest, by Ptolemy. It was still the prevailing belief in the 16th century. And Ptolemy, being an astronomer, as well as a mathematician, he says, I wonder if there's a better way this could happen so we don't have these little dark matter things out there. And he realized that if we change the center of the universe from being the Earth to the Sun, that now we could have these movable stars, which at this point have come to be known as planets, they can be making circular orbits around the Sun. And the Earth would just be another one of these planets orbiting around the Sun. And so what he did was he changed us from a geocentric concept of the universe to a heliocentric, a sun-centered view of the universe. And because these orbits went at different speeds, that is what was causing the effect of the retrograde motion. So Copernicus changed us totally away from the geocentric model to the heliocentric model. The planets are going in circular orbits around the Sun. The Moon is an exception. It's going in a circular orbit around the Earth. The only thing that's still the same from the old Ptolemaic model was that sphere of constellations, those fixed stars out there in the outermost sphere. As far as anybody knew, that sphere still existed out there. It was out there somewhere beyond the orbit of Saturn. We didn't know where, but it was out there. And so we still had an absolute space. It was bounded by the Sun in the center now, and that fixed sphere of constellations. Now, Copernicus published his findings in what was called On the Revolutions of the Celestial Spheres. The question that came up is, he's a Catholic. In fact, he's a Catholic clergyman. And the Roman Catholic Church, which is pretty much the power during the Middle Ages, is very much believing that man is the center of the universe. Mankind, God created man in his image, and man is the center of the universe. So while we had the geocentric view, there was not a problem. But now all of a sudden we have a heliocentric, where the sun is the center of the universe. So the question is, why isn't the Catholic Church going after Copernicus? Well, there's a couple reasons. First, this is a brand new idea. So very few people know about this idea. In the world of science, it can take anywhere from 50 to 100 years for a new idea to take hold in the scientific community. Second of all, Copernicus says, okay, I'm going to flatter the Pope with this publication, and he dedicates it to Pope Paul III. So that kind of keeps the Catholic Church at bay a little bit. But the main reason he isn't prosecuted was that the year that the book was published, in 1543, that was also the same year that Copernicus died. And so Copernicus wasn't around for the church to prosecute. In the next generation after Copernicus, we have another famous astronomer. His name is Tycho Brahe. And he's Danish. Not so much of a mathematician, but very much an astronomer. And what he did was he took very meticulous notes about his observations of the heavens, about where the stars are, where the planets are, where the moon is, where the sun is, so that he had the best data in the world on the heavenly bodies. But he wouldn't share it with anybody. Fortunately, he had an assistant. And that assistant was Johannes Kepler. And when Tycho wanted something analyzed, he would give the data to Kepler and told Kepler to analyze it. Kepler was an astronomer, but also a mathematician. Now, when Tycho died, all of this data got inherited by Kepler. And so when Kepler got hold of this information and started analyzing it all, he suddenly realized that, well, Copernicus was almost right. You can think of the universe as being centered on the sun, but instead of circular orbits around the sun, the planets did elliptical orbits around the sun. And so this was Kepler's change to Copernicus's model. The orbits were elliptical, and he had the mathematics behind it to show why the orbits were elliptical. Okay, so why is the Catholic Church not after Kepler? Well, at this time, we just got finished having the Protestant Reformation. And Martin Luther, all of his followers, had pulled away from the Catholic Church and created the Lutheran religion. And the Lutherans did not consider themselves under the authority of the Pope. And most of Germany followed in this move to Lutheranism. Kepler was German, and so he was Lutheran. Therefore, he was not subject to the authority of the Pope. Therefore, he could not be prosecuted by the Pope. Our next person of interest is Galileo Galilei. He was a contemporary of Kepler. He was interested in mathematics and astronomy and something called natural philosophy, which is the forerunner of the field of physics. We don't have physics quite yet. It's still being called natural philosophy at this point. And what Galileo was interested in was something a little bit different from Kepler. He didn't care about whether or not we had circular orbits or elliptical orbits. He was concerned about which idea was correct, the geocentric or the heliocentric. In fact, his paper was called A Dialogue Concerning the Two Chief World Systems. This was published in 1632. And what were the two chief world systems? Well, one was the geocentric universe of Ptolemy, as portrayed in the Almagest. The other one is the heliocentric view put forward by Copernicus. And the question of the day was, if the Earth is moving around the sun, shouldn't we feel the Earth moving? Remember, Aristotle, we had geocentric because standing on the Earth, we don't feel anything moving. But yet, Copernicus is proposing that the Earth is indeed in motion. So should we be able to run tests to determine if the Earth is in motion? So for example, we could have a ship, and eventually we'll call this Galileo's ship. And this ship is pointed east and west, and it's got cannons both at the front and the back of the ship. And if we fire both cannons, will the cannonballs go different distances because the Earth has moved? You know, from the time of firing the cannons to when the cannonballs land, will the Earth have moved a sufficient distance to cause the distance that the cannonballs fly to be different? And Galileo will say no. There will be no change in the distance. And he will say this is because of a principle of relativity. This is the first time that we have this concept of the principle of relativity. And it comes about because of this change from a geocentric universe to a heliocentric universe, and the question of whether or not you can tell the Earth is moving. Okay, so what does Galileo do? Well, he goes to the top of the tallest mast of a ship, and he drops a ball down the side of the mast. And the question is, will it veer to the left or the right, or will it go straight down? Well, the cannonball went straight down, indicating that we seem to have this principle of relativity, whereas in our local area, we cannot tell the difference whether or not we are in one frame of reference or a different moving frame of reference. Furthermore, he proposes some thought experiments. He says, let's suppose that you're inside of this ship, this Galileo's ship, and there are no windows in the ship, so you cannot tell if the ship is moving or standing still. And the ship is floating on still water. Now the question is, it's not so much is the earth moving around the sun, but is the ship tied up at the dock, or is the ship floating along with the current in a straight line at a set velocity? Can the person inside the ship determine that through experimentation, whether the ship is standing still or moving at a set velocity? And he suggests 3 different kinds of experiments. One involves birds flying. One involves water dripping down. Another involves incense burning and smoke coming up. And the question is, if the ship is moving, should the birds congregate to one side or another of the inside of this ship? Should the water veer left or right as it drips down? Should the smoke veer left or right as it goes up? And he says, no, in all cases, whether or not you're standing still at the dock or the ship is moving, the birds will fill the cabin, the water will go straight down, and the smoke will go straight up. This is that principle of relativity where you cannot tell through experimentation whether or not you are moving or not. All right, so we said that Galileo was an Italian Catholic. So, he published his document in 1632. Well, the next year in 1633, Galileo is dragged before the Roman Inquisition. And the Roman Inquisition wants Galileo to rescind his views that we have a heliocentric system. Galileo refuses, and he's put under house arrest for the remainder of his life, which is about 9 years. It would take several centuries before the Catholic Church finally reversed that opinion and said that Galileo was right. Our next person was born the year after Galileo died. This was Sir Isaac Newton. Now, Newton was born in England, and if you know your church history, you know that King Henry VIII had pulled the Catholic Church out of the Roman world and set up his own Church of England, in which the king is the head of the church. And so Isaac Newton, his parents are Anglican, he's Anglican, therefore they are not under the authority of the Pope, so Newton's free to do whatever he wants. Now again, Newton, like everybody else, mathematician, astronomer, but now we also call him a physicist. But you can tell that we're in that transition period because Newton's work on this subject was called The Mathematical Principles of Natural Philosophy. He published it in 1687. We actually call it the Principia today. Principia is Latin for principles. And what the Principia contains is Newton's view of the principle of relativity. So he's taking up the idea of Galileo now and putting it in context of what he thinks this principle of relativity means. First of all, he says that we have absolute space. This idea of absolute space comes from the fact that we still think in this time period that there is this outer sphere of fixed stars and constellations. It's still someplace out there beyond the orbit of Saturn. We don't know how far, but it still exists there, and that gives us a fixed volume of space. And so there is an absolute space. He indicates that a frame of reference is in uniform motion to this absolute space. We kind of have to look at, well, what's standing still? Well, we still have the sun standing still. This is a heliocentric system. So the sun is standing still, and we can measure the velocities of everything else based off of the sun standing still. So every object is either at rest, like the sun, or it's in motion at some absolute speed. Not a relative speed, but an absolute speed that can be calculated. He adds the fact that he thinks that there is an absolute time, that throughout this universe, everything operates off of a set time. There is simultaneity between everything, between that, sphere of fixed stars, the planets, the earth, the moon, the sun, that if anything happens on one of these, that there is a possibility of a simultaneous event on something else. So time is very much tied up being simultaneous throughout the entire universe. As far as what physical laws were valid in each frame of reference, Newton argued that it was his first law of motion. What was his first law? Well, that's the one that deals with inertia. An object in motion stays in motion unless operated by a force. He says that law will be valid in every frame of reference. So we could call them inertial frames of reference at this point. They didn't yet at this time, but we're heading in that direction. Another thing that he added new to this concept was the concept of a Galilean transformation. What's a Galilean transformation? Well, everybody thought the universe followed Euclidean geometry. Euclidean geometry is what we learn in our high school geometry class. And what's involved with the Euclidean geometry? Well, you can have an origin. You can place that origin any place. Suppose you put it at the sun. It's the center of the universe. And that origin has coming out of it 3 different dimensions. You've got length, width, and height. And they are all 90 degrees to each other, or what we would call orthogonal. So if we wanted to find the relationship between one frame of reference and another frame of reference, all we had to do was calculate the length, the width, and the height from one frame to the other. That is a Galilean transformation. Newton also still felt in this concept of ether out there in space. We still had nothing indicating that space was empty. Newton was firmly on board with the idea that space was filled with ether. And one of the other interests of Newton was light. And in fact, he published another book called Optics. He published this in 1704, in which he put forward the idea of the corpuscular theory of light. Now, what is a corpuscle? Well, you can think of blood corpuscles. A corpuscle is an entity or particle or whatever you want to call it that has certain properties. And what kind of properties did Newton give to it? Well, he said that each corpuscle would have a certain color associated with it, and that each color had a certain velocity associated with it. And he said that we saw white light because the air, everything was filled with all these different colored corpuscles, and when you have all the corpuscles together, it makes white light. Now, how did he prove this? Well, he took the white light, he passed it through a prism, and if you understand optics with a prism, it's going to break the white light into the spectrum of colors, like the rainbow. And so these corpuscles, because they're traveling at different speeds, are going to be bent at a different angle by the prism. And that's why the light gets spread out into this spectrum that goes from a deep purple to a bright red. Now, Newton had no idea that the spectrum continued into the ultraviolet and infrared range. That won't happen until around 1800. So Newton thought that the entire spectrum was the visible light that he saw. But he expanded on this experiment by taking this spectrum, sending it through another prism, and getting back white light. So he could break the white light into colors and send it back together again into a white light. That was his corpuscular theory of light. There was a second idea out there at the same time as Newton's idea, and that was put forward by Christian Huygens. Huygens was a Dutch physicist, and Huygens put out a treatise called the Treatise on Light in 1690. And in that treaty, Huygens proposed that light actually functioned like a wave rather than a particle. His ideas were not immediately accepted. The main reason was because Newton had this experiment where he could show the corpuscles being spread out into a spectrum and brought back together. But eventually, in the early 1800s, people started to accept Huygens' ideas. And in fact, today, physicists will argue that light operates both like a particle and like a wave. And so it incorporates both the ideas of Isaac Newton as well as the ideas of Christian Huygens. All right, when Newton spread his light into the multiple colors, the colors just sort of blended from one color to the next, pretty much like what we see in the rainbow. In the late 1700s, early 1800s, there was another man called Joseph Ritter von Fraunhofer. He was Bavarian, and he was known for his high-quality glass. He had the highest quality glass in Europe, much finer quality than anything that Isaac Newton had. And what Fraunhofer did with his higher quality glass is that he also made a prism, shone the light through the prism, had it spread out into the spectrum, and what he got was a much more sharply defined spectrum. And one of the things that they found in this much clearer spectrum were little dark bars at various places within the spectrum. These dark bars got to be known as Fraunhofer lines, named after Fraunhofer. That was the way things worked in those days. You discover something, you get your name associated with it. Now, scientists at first didn't know what these Fraunhofer lines represented, but eventually they figured out that it represented what kind of gas the light had gone through before it got to the prism. Because if they shine light through hydrogen gas, they would get one set of Fraunhofer lines. If they sent the light through oxygen, they would get a different set of Fraunhofer lines. So they knew that these Fraunhofer lines dealt with what kind of gas the light was traveling through. One of the other things that they noticed as they looked at various stars is that these Fraunhofer lines as a whole tended to shift left and right. And they needed to get an explanation of what this left and right shifting of these Fraunhofer lines was all about. So that brings us up to our next gentleman, who was an Austrian named Christian Andreas Doppler. You can imagine what he's famous for. Obviously, it's the Doppler effect. Okay, he again was a mathematician, physicist, and he published a paper called On the Colored Light of the Binary Stars and Some Other Stars of the Heavens. This was published in 1842. And what he postulated was that the observed frequency of waves in the light depended on the relative speed of the source and the observer. Okay, we know that today as the Doppler effect. Okay, so what is the Doppler effect? Well, we probably all learned the Doppler effect using the same example back in high school physics. The idea is that you're standing at a train crossing. Okay, a train is coming and it's blowing its whistle at you. And as the train is approaching you, you hear a higher pitched sound. As soon as the train passes you, that higher pitched sound suddenly goes to a lower pitched sound as the train is past you. You know, it's kind of like a sound. That's the Doppler effect. Now, what is it? Well, the idea is that we have sound going as compression waves through the air. And out in front of the train, these compression waves are being pressed closer together by the fact that the train is moving. And so these compression waves that are being pressed closer together are causing a higher pitch. Behind the train, the waves are being spread out. And the spread out waves is causing a lower pitch. And so that's why when you're in front of the train, you're hearing this higher pitch sound. And after the train passes, now all of a sudden you're hearing these lower pitch sounds. That is the Doppler effect. But the question here is that Doppler, when he came up with this idea, he wasn't talking about sound. He was talking about light. So how do you explain the Doppler effect for light? Well, remember that scientists still think the universe is filled with ether. And that light is being transmitted by compression waves through the ether. So just like you can have the Doppler effect in sound, you can have the Doppler effect in light. If you take a look at this diagram, you've got a star moving towards the Earth. And what's happening is the waves out in front of the star are being bunched up together, and the waves behind the star are being stretched out. Well, what does this mean in terms of light? Well, the bunched up waves means you have a higher frequency. And a higher frequency means that you're dealing with a blue shifting of the light. You know, the blue end of a spectrum has a higher frequency than the red end. The red end has a lower frequency. It's got longer wavelengths, lower frequency. Blue end, shorter wavelengths, higher frequency. And so when the star is moving towards the Earth, the light from the star is going to turn bluer. If you're on the other side of the star, where the waves are spread apart and the star is moving away from you, the light from the star will turn redder. And that's what Doppler thought when he was observing these stars out there that had different colors, that it was this redshift and blue shift. Okay, so what exactly is redshift and blue shift? Well, it comes about as a result of these Fraunhofer lines. If you take a look at this diagram, the spectrum in the middle will assume to be the standard location of the Fraunhofer lines for a particular spectrum. And it's as if things are not moving. On the top, you've got the Fraunhofer lines shifted towards the blue end of the spectrum. This is a blue shift and is generally associated with something moving, or light moving towards you. In the bottom spectrum, you have the Fraunhofer lines shifted towards the red end. This is redshift and indicates that the star is moving away from you. Okay? So it was these Fraunhofer lines and these movement of these Fraunhofer lines that gave us the concept of redshift and blue shift. All right, well, we're going to move on to another contemporary of Christian Doppler. His name was Armand Hippolyte Louis Fizeau. Fizeau was French. He was a French physicist. And he was very much looking at the work of Doppler. And in fact, doing a lot of the same things as Doppler, correcting Doppler's mistakes and things. And if you happen to go to France and be in France, they don't call it the Doppler effect there. There in France, it's called the Doppler Fizeau effect. The rest of the world calls it the Doppler effect. But Fizeau was very much involved with this effect. And one of the things that Fizeau did was that he developed a mathematical theorem that underlined the principles of this light and being able to predict red shifts and blue shifts as a result. And here we're looking at this Doppler effect formula. And what you should notice is that it is a formula that kind of takes us from the frequency of the sender to the frequency of the receiver. Now let's go back to the train example. The frequency of the sender is going to be a train whistle. The train is moving, it's sending out this sound wave at a particular frequency. The frequency of the receiver is the person at the railroad crossing who is hearing this sound. And we know that we're hearing a different frequency from what is being sent out by the train horn. So how do we calculate this difference? Well, it's the stuff on the right-hand side of this equation. And what kinds of things are involved in this? Well, first of all, you're talking about the velocity of the receiver. Well, the receiver is used standing at the railroad crossing, so in this example, it's 0. Doesn't have to be, you could be walking, but right now, if you're standing there, you've got a 0 velocity. You've got the velocity of the sender. What's that? Well, that's the movement of the train. How fast is the train coming down the track? And then you've got the velocity of the medium. What is the velocity of the medium? Well, the medium for the train is air. And we have something called the sound barrier. How fast does sound go through air? You know, we talk about jets that can break the sound barrier. Well, here we're talking about how fast does sound move through the air. And depending upon the temperature, humidity, different things, it travels at a specific rate through the air. So that's how it works for sound. Now what about light? Well, the same things are going to happen. You've got your velocity of your sender, which is some star that's moving. You have the velocity of the receiver, which is the observer, who could be standing still. And you have the velocity of the medium. Well, what's the medium? The medium is this ether out there. Now, we don't have any clue as to what is the speed of light through the ether, but we think it's a compression wave just like sound, and so there is some value for this movement of light, and we think it's going to be this value c. You know, this is the thinking at the time, that the Doppler effect for light is the same as the Doppler effect for sound. It's just we have a different medium. We have ether instead of air. So we've got this idea of the Doppler effect for both sound and light. We need to verify this, and so there are people that did experiments to verify in a laboratory setting that the Doppler effect, these frequency changes, were due to velocity changes. Our first gentleman is called Buys Ballot. He was a Dutch meteorologist, and what Buys Ballot did was that he set up musicians on a train, and all these musicians would play a certain calibrated note. And he would have the train moving along with these musicians playing this note, and by the side of the track he would have an observer that would pick up the frequency of this note being played. And what he found was that as the train was approaching, he would hear this note as a higher pitched note. As the train was passing by, after it was going past him, all of a sudden that pitch was a lower pitch. So he was able to verify in a laboratory setting that the Doppler effect for sound was based on the velocity of the train. What about for light? Well, there was a Russian astronomer named Aristarka Belopolsky who was a very fine instrument maker. And what he did was he took light from the sun. Okay, it had a set velocity in terms of a sender, but he could adjust the velocity of the receiver, and he did that through a set of rotating mirrors. And by rotating the mirrors in a certain way, he could simulate the receiver moving at different speeds. And what he observed was this redshift and blueshift of these Fraunhofer lines. And so this verified that the speed of the receiver, at least, was affecting the frequency of the light that you observe. So this was a laboratory confirmation for the Doppler effect for light. Okay, so at this point then, we have the belief firmly entrenched that the Doppler effect functions both for sound and for light. And they both are measuring velocity. things moving. All right, we're going to switch back now to the nature of the universe. We left off with Isaac Newton, and we've got this absolute space where we've got this fixed sphere of stars. We still need to break that idea, because we know today that there is no fixed sphere of stars out there. And so it takes us up to a gentleman called William Herschel. He was German born, but he migrated to Great Britain. He was an astronomer. And what Herschel did was he built his own telescope. And at the time, it was the largest telescope in the world. And one of the things that he did with this telescope was he found a new planet. He discovered Uranus. Up until this point, from ancient times, scientists were only aware of the planets Mercury, Venus, Mars, Jupiter, and Saturn. They were aware of them because they were visible to the naked eye. But now all of a sudden with this telescope, Herschel can see another planet, Uranus. This made Herschel world famous. Now, Herschel was famous for some other things also. He also discovered over 2,400 objects in space that were not points of light. In fact, they were fuzzy in nature. And he would call these nebula. And he had stars and you had nebula out there. And one of the things that he figured out was that some things were in front of and behind other things. So therefore, we did not have this one celestial sphere of fixed constellations. We had stars and nebula at different distances from the Earth. And in fact, he called this a galaxy. In fact, he named that galaxy. He called it the Milky Way galaxy. And so under Herschel, we have another paradigm shift now where we don't have the geocentric of Ptolemy, we don't have the heliocentric of Copernicus, we now have a galactocentric universe, the one of William Herschel. And he published a picture of this galaxy in the Philosophical Transactions of the Royal Society in 1785. And he said that our sun is but one of the stars in this galaxy. And our sun rotates around the middle of the galaxy. So the center of the universe is the center of the Milky Way galaxy. There was only one galaxy in the universe, and it was the Milky Way. And so what we had was a galactocentric universe. So by the middle of the 19th century, in the middle of the 1800s, scientists thought they had a pretty good idea on the nature of the universe, on the nature of the principle of relativity, on the nature of light. You know, the universe was no longer an absolute space. It was open. It went on infinitely in all directions. We also think that the principle of relativity applies to all of these different inertial frames of reference. By this time, they are called inertial frames of reference. And we didn't care that there was nothing standing still in the universe. All we cared about was the fact that these inertial frames of reference were in relative motion to each other. And this is what Einstein's going to pick up on, is this idea of nothing standing still and everything in relative motion to each other. That's going to be this principle of relativity. And we also thought we had a good idea on the nature of light. That we had this ether in outer space, that light was being transmitted through this ether by compression waves. We were pretty sure the speed of that light was the constant c, because people had been starting to perform experiments on that. And so we were pretty sure that redshift and blueshift indicated velocity in terms of these stars moving towards or away from us. And that was the status in the middle of the 1800s. Little did they know that this world was going to change drastically in what is discovered in the last half of the 1800s. We thank you for your time listening to this lecture. We look forward to you on the next lecture, where we'll take up that fact of the velocity of light and whether or not it's a fixed velocity or if it's a non-constant velocity.